So sample problem 8.4 is another problem like we saw in sample problem 8.3 where we were ranking things by atomic size. Now we're going to rank things by first ionization energy. So again, thinking about this, when you think about the first ionization energy, you're basically removing an electron and asking how much do you want to be a cation? So how much do you want to be a cation? How much do you want to be positively charged? And one thing that's interesting to note is that for all species, this energy is going to be a positive value. If we think about kind of an enthalpy value, these are all going to be values that are kind of unfavorable. They're not spontaneous. It's going to take energy to remove an electron. So even things that are on the left side of the periodic table are metals that like to give up electrons. It's still going to be an unfavorable process to remove an electron from an atom. That attractive force that's holding it there is so great. So one of the things that we need to think about is, okay, what are some of the things that make an atom want to hold on to its electron? Well, remember, we said holding on to electrons basically has to do with how close they feel those protons within that nucleus. So here's going to be the trends for what we see here for ionization energy. Ionization energy increases as you go up and increases as you go across. Well, if we kind of remember our last trend here, that's actually the opposite of what we saw there. And so these trends are kind of related, that if you think about it, what's happening as we become smaller and smaller is those electrons are closer to that nucleus, so they're going to be held tighter. So thought of the other way, the bigger an atom becomes, the easier it is to take an electron away because it's not feeling that positive charge in the nucleus as well. So in the back of our mind, we're going to keep size trends because they kind of parallel what we see here. In terms of the largest atoms are going to have the smallest ionization energies because those electrons are going to be the easiest to remove. Okay, so we're going to use kind of the same process that we used in our previous problem to kind of compare and use our periodic table and see what we're comparing. So if we compare krypton and argon and helium, we have three things that are all in the same column. So again, all being in the same column. From periodic lingo, that's all in the same group. Okay, so we need to just think about, well, who's going to be the smallest? Because the smallest is going to have the largest ionization energy. And this problem asks us to rank the elements in order of decreasing first ionization energy. So the largest ionization energy is going to come first. That's going to come from our smallest atom because those electrons in helium are closest to the positively charged nucleus, and so they're going to be attracted the most and held the tightest. So when we look at this, helium is going to become first, then argon, then krypton. Okay, so the trend is going to be helium will have the largest ionization energy, then argon, and then krypton. All right, looking at the next trend, we've got antimony, tellurium, and then tin. So antimony, tellurium, and tin. So here's this set of three. So again, we're looking at three things that are all within the same period. So maybe you're seeing the same kind of examples as we had with our previous problem, apples to apples, and then we're going to see two apples to oranges comparisons. So these are all within the same row of the periodic table, remembering that we get smaller as we go from left to right. Tellurium, for example, is going to be the smallest of these. It's going to have its electrons held most tightly. In addition, we can think about the fact that there's additional protons that are present here. And when we have more protons, that's going to create a greater attractive force for those electrons. So we're going to have the largest ionization energy with tellurium, and then we're going to see antimony, and then we're going to see tin. Okay, so that's the trend we'll see for this set of three that are all in the same row of the periodic table. Again, our next example here, potassium, calcium, and rubidium. So potassium, calcium, rubidium. Remembering that the change in row is going to have the greatest effect here. The electrons are furthest away for the N equals 5 rubidium, so that's going to have the smallest ionization energy. So as we compare potassium and calcium, Again, calcium is going to be smaller, so this guy is going to actually have the largest ionization energy. Hardest to remove electrons from calcium. So calcium is again going to be greater than potassium. And then once we jump down a row on the periodic table, we have the easiest electrons to remove in this group of 3. Okay, our last example here deals with, sorry, my cat there, xenon and iodine and then cesium. So again, 2 in the same n equals 5 row here, and then we have 1 in the n equals 6 row here. So again, the jump to n equals 6 is always going to have the largest effect. So cesium in that case is going to have the smallest ionization energy. And then comparing these two, okay, xenon is again going to be the smallest here, so that's going to have the largest ionization energy. And then we'll see iodine in the middle. So again, we're going to see a lot of problems in this chapter that ask us to think about trends in the periodic table, and they should make sense.